Ashraf and Kambao, you can hear me loud and clear, right?
Yes, clear.
Okay,
Yes.
that's great. Okay, now let's continue with our lesson. We actually missed one lesson last Wednesday, but let's move on. Let's see if we can cover all chapters within, if we don't need makeup class, then we'll go ahead. All right. Because actually, I've already taken your tutorial hours as well for the class. So therefore, in case we don't need additional or makeup class for last Wednesday, then we'll go ahead then. Now, am I right to say that the last lesson or activity that we stopped at is activity 2.19? Am I right? Which I have assigned or Atika to help us. Agree? Do you guys agree in it?
Yes.
Yes.
Okay, great. All right. Okay, now let's see. This is the activity, right? Okay. Now, Atika, are you ready to go ahead? Atika?
Yes, doctor.
Okay, I'm going to stop presenting. Then I'll pass the screen to you. Atika, please.
Okay, determine the depth of flow Y naught in the channel if rate of flow is 23 meter cube per second, meaning coefficient N and bed slope are 0.015 and 0.0015 respectively.
Okay, Atika, I
Yes.
wanted to ask you one thing. Why do you use why not? Well, maybe the question give you, what's the difference between why and why not that you are using here?
Y is for Y2 tu
Uh-huh.
untuk kedalaman yang rectangular ni.
Okay.
Yang Y naught adalah untuk ketinggian keseluruhan.
Okay. Why not juga untuk simbol untuk ukur dalam aliran seragam, betul tak? Uniform flow lah. Depth of uniform flow. That's why we use the symbol of why not. Agree
Okay.
Okay.
Agree.
Kalau Y sahaja, maknanya untuk ukur dalam yang termasuk ukur dalam uniform flow lah. Alright. So why not do specifically untuk depth of uniform flow untuk ukur dalam aliran seragam. Okay, terima kasih. Go ahead please. Thank you.
Okay. Okay, daripada soalan ni dah diberi nilai Q iaitu 23 meter cube per second, nilai N 0.015 dan juga nilai S0 0.0015. Lepas tu daripada gambar aja ni dah diberi nilai B 4.5 meter, nilai Y1 iaitu 2.25 meter dan juga nilai Z kita boleh cari guna sudut 45 darjah ni. Iaitu
Okay.
Z sama dengan
Atika nak tanya, macam mana you dapat Y1 sama dengan 2.25? Dia mula-mula tak bagi kan? Betul?
kat slide ni memang dah ada 2.25.
Oh, dekat slide tu memang dah ada 2.25 Oh, okay. Macam ni sebenarnya mungkin saya tersilap bagi. Katakanlah kalaulah let's say if 2.25 is not given but only the top width is given which is 4.5 meter. Berdasarkan sudut 45 darjah, kita tahu dia punya side slope yang triangular section tu ialah 1 to 1, betul tak? Jadi lebar sebahagian triangular section would be half of 4.5. Maknanya 2.25. Jadi Y1 pun secara because the side slope is 1 to 1, secara automatic pun 2.25 meter. Betul
Betul.
Okay, alright. Okay, thank you Atika. Go ahead please.
Okay. Nilai Z kita boleh cari iaitu 1 over tangent 45. Jadi Z sama dengan 1. Okay, kemudian kita cari dia punya area untuk triangular tambah dengan untuk rectangle ni. Lepas tu kita guna formula ni, masukkan nilai dia, dan dapat jawapan 5.0625 tambah 4.5 Y2. Okay, kemudian kita cari dia punya weighted parameter. Weighted parameter kita kira untuk bahagian ni saja. Okay, lepas tu kita guna formula ni, and then masukkan dia punya nilai, dapat 6.364 tambah 2Y2. Kemudian untuk cari nilai Y2, kita guna formula AR kuasa 2/3 sama dengan QN per S0 kuasa 1/2. Okay, masukkan dia punya nilai. Dapat jawapan 5.0625 tambah 4.5 Y2 kuasa 5/3 bahagi 6.364 tambah 2Y2 kuasa 2/3 sama dengan 8.9079. Okay, kemudian saya guna method trial and error. Mula-mula saya guna nilai Y2 ni sama dengan 1, saya dapat 10.46. Okay, kemudian saya guna 0.5, saya dapat nilai 7.278. Kemudian saya guna nilai 0.7, dapat 8.526. Kemudian 0.76 dapat 8.905. 8.905 ni hampir sama dengan 8.9079. So saya ambil Y2 sama dengan 0.76. Tapi dia nak Y0. Y0 sama dengan Y2 tambah Y1. Jadi 0.76 tambah 2.25. Y0 sama dengan 3.01 meter.
Okay, very good Atika, thank you. Ini jawapan Atika Y0 sama dengan 3.01 meter, betul? Atika?
Ya.
Ini jawapan Atika Y0 sama
Ya.
dengan, okay. Atika, saya ada satu soalan. Kenapa Atika guna table trial and error, tak guna calculator terus?
Saya nak trial and error.
Okay, maknanya ada cuba guna calculator tak check jawapan?
Belum.
Okay, tapi calculator lagi cepat kan? Maknanya you key in the formula di section factor expression, kemudian boleh dapat terus kan, tekan solve kan? Alright, okay, great. Thank you Atika.
Okay.
Alright, thanks a lot. Okay, now let's go through a bit thanks Atika. Could I share? Okay, I'm going to share my slide right now. Okay. Okay. Now, if you look at this, right? Yes, I have the same answer as yours, Atika. Congratulations to you. You have got the right answer. Well, we got the same answer lah. Oh, basically you got the right answer lah. Okay, now, if you look at my steps here, what I did here is, okay, now, sometimes, well, just now, earlier I told you this probably would not be provided. It will only provide you the side slope as well as the top width. Therefore, you can actually figure this out yourself, all right? Okay, don't mind that, right? It's, okay, couldn't delete this. Okay, now, if it's just giving you the side slope, basically you can find this already. That means the dimension of the triangular section at the bottom. Here's the thing. Sometimes the diagram give you such a, flow area. However, we don't know whether the depth of flow is just within the triangular section, this section here, all right? Or does it exceed the triangular section? But right now, if you look at this diagram, we will say yes, it will exceed. That means our formula for A and P, I don't know what's wrong. Okay, it doesn't matter. Okay, that means our formula for A and P, okay, A and P would actually include this part, which is the rectangular part. Okay, now however, okay, if I want to, this is, I guess this is probably will take you a few minutes to check. What I'll do is I assume that the discharge actually fill up the entire triangular section. I know that as y increases, my q will increase as well. All right. What I did is I tried to find the triangular section discharge. Okay, the discharge which go over the triangular section, filling it up until 2.25 meter. So if you look at here, Q1, which is a section 1, the triangular one, is actually 0.4346. Of course, my flow area and my wetted perimeter, I just consider the triangular section. So what I found is the discharge for the triangular section is 0.4346. The discharge given in the question is 23 cubic. So what I say, what I have found out is the discharge is definitely would cover both area or both section, which is a triangular and rectangular. I say here the flow should be beyond the triangular section. That means it will actually fill up the rectangular section as well. So what I did here is I actually substitute the formula for, the compound section. That means the triangular as well as the rectangular. So I have my flow area formula. Of course, my Y1, I replace it with 2.25 because I already assume it to be fully covered. Then I have my rectangular flow area here. So this is my formula in terms of Y2. Then my wetted perimeter, of course, I'll include this triangular as well as the rectangular section. Of course, my rectangular section would be in terms of the depth of Y2, while my triangular would be in terms of the depth would be in terms of Y1. Substituting, still assuming that this is fully flow, then I have this expression, which is my wetted perimeter is equal to 6.364 plus 2y2. Now, because Manning coefficient is given in the question, all right? So I'll use the Manning flow resistance equation. And then rearranging the formula where I put the section factor, which is the function of depth, on one as the subject of the equation. So substituting A and P, okay, and I substitute Qn and S naught, I'm going to have this. Yes, Atika, thank you. You have shown us a try and error. That is good. You have try to do the table. That is actually helpful to understand how the process of try and error are conducted. So solving this, okay, you cannot solve it directly, so you have to do try and error. You will get y2 equals to 0.7601. Now, bear in mind y2 is just the depth within the rectangular section. So therefore, if you want to, since the question asks for y naught, you have to include this y1 here, which is actually 2.25. So therefore, y naught is 2.25 plus 0.76. You'll have 3.01 meter. Okay. So anyone has any questions so far? No? If you don't have any question, we'll go ahead. We'll continue our lesson. Now, this subtopic is about, the simplification that we are going to use when we consider when the problem involve very wide rectangular channel. Now, the word, if you look at this, there's this, you have this term very, wide rectangular channel. Now, how do you classify it as very wide channel? Now, very wide channel is when the width of the channel is very wide respective to the depth of flow. Why not? So if you take the ratio of y naught divided by b, it will be much smaller than 0.02. Okay, that means it's 1 to 100 lah, basically. Now, for very wide channel, since y naught over b is small, therefore r is almost equal to y naught, or simply, okay, in this case, very wide channel, sometimes the question just say very wide channel, okay, you can actually use r equals to y naught. Now let me show you an example. I'm going to present an example to you. Okay, now let's look at this. If in the case of very wide channel, let's say I have a rectangular channel. Okay. Now for very wide channel, we'll just assume in subsequent question, we'll just assume it is a almost rectangular section. Let's just assume the depth of flow is 0.1 meter here in this case. And then the width of the channel is 10 meter. This is, smaller than 0.02, right? Okay, the ratio. So what we are going to have here is, let's just say, I'm going to prove that we can actually use R equals to Y in this case. So in this case, our A is BY, which is 1 meter squared. That means 10 times 0.1. Then our method parameter would be b plus 2y. That means is b plus 2y is 10.2 meter. So there you have it. Now what is R? R is A divided by P, which is 1 divided by 10.2. Now what will you get is 0.0980 meter. Now therefore is almost equal to 0.1 meter, which is your Y lah, basically. Alright, the depth of flow. Now even if this is much smaller, then definitely R is equal to R is almost equals to Y. Okay, then all right. Okay, R is therefore I have shown you that in this case where your Y over B is much smaller than 0.02, you could actually use the approximation of R equals to Y. Furthermore, look at this. You know, if a small number, you have a multiplication, all right, value, that small number is going to affect the multiplication, or it will affect A, basically. If you have a small value, if you have addition, right, this is actually, less likely to affect weighted parameter. Okay, therefore, you have R is almost equals to, if you cancel B lah, basically, since P is almost equal to B, okay, then you will have R is almost equal to Y lah, basically, since you have A divided by P, right? Okay, so this is almost equal to Y. That's the concept of it, all right? Okay, then let's go back. we are going to learn another term, which is the discharge over unit width. Okay, now this discharge over unit width, okay, is actually normally used in rectangular channels. Okay, why? Because rectangular channel has a fixed width. Not like trapezoidal channel. It has bottom width, it has a top width. All right, so it's not standard throughout the depth of the channel. Now, what is discharge over unit width? Is actually this symbol here, which is discharge divided by the width of the channel. So the unit would be meter cube over second, which is this unit, the discharge, divided by meter, which is the unit of B. You can rewrite this formula here, okay? All right, in terms of Q equals to YV. How do you do that is, you know that this is Q is, this is A V divided by B. Okay. Now, for rectangular channel, this is BY. Okay. So what you'll have here is YV. Okay. This is A. All right. So therefore, you'll get back. Okay. Q equals to YV. This, now remember, this only applies for rectangular channel as well as this lah. All right. The simplification and the discharge over unit width only applies for rectangular channel. Now, sometimes you also find we write our unit as in terms of meter squared over second, because this is a simplification. Basically, meter cube divided by meter, right? We have meter squared over second. So be careful. Sometimes in the question will give you discharge, but will give you this unit. This is actually discharge over unit width. All right. Okay, then. Rodney, are you ready to, solve this question here?
Ready, Doctor.
Ready, yeah? Okay. So I'm going to stop presenting. I'll pass the screen to you then.
Okay, jap. Ada nampak?
Yes.
Okay.
All right.
Saya
Very
guna
clear.
bahasa Melayu. Okey, kalau kita tengok pada aktiviti 2.20, dia ada bagi B 60 meter, Q dia 2.5 meter cube per second, S0 dia 0.05 dan N dia 0.013. So dekat soalan dia cakap very wide channel. So saya assume dia rectangular lah untuk cari Y not dia ni. Since dia very wide channel, sama macam doktor tadi, dia R sama dengan Y. So saya pakai Manning equation. Lepas tu saya susun dia Q sama dengan Y not V. Lepas tu Q, Y 1 per N, R 2 per 3. S not dia 1 per 2. Lepas tu saya susun lagi Q 1 per N, Y not 5 per 3.
Okay, Rodney, I think between your second and third equation, you have substitute R equals to Y already, Then you combine the Y. Okay, great. Please
Saya
continue.
combine Y. So S not dia 1 per 2 juga. So Q kita tahu 2.5 equal to 1. N kita tadi 0.013. Y not kita masih sama, darab dengan 0.005 1 per 2, iaitu S not kita tadi. Lepas tu saya pindahkan Y not dia ke tepi ni. Lepas tu saya darab masuk 0.013 darab dengan 2.5 per 0.005 1 per 2. So bagaimana saya hilangkan Y not ni jadi 1? Saya darab balik dengan yang terbalik tu sama dengan 0.459 3 per 5 untuk hilangkan 5 per 3 dia ni. So jawapan saya 0.6272. Okay.
Okay, thank you, Rodney. Very clear. Alright, thanks. And
Thank
you
you,
have
Doctor.
yeah, your working step are very systematic as well. Very good, clear. Now let's continue. I think you don't need further explanation, right? Rodney has explained well, right? Okay. So let's see. Okay. Now we got the same answer, right, Rodney? 0.6272 can?
Yeah.
Alright. Yeah. I think mine is yours is you explain better. Okay. Mine is I straight away jump. I guess I miss few steps as well. Alright. Okay. Now let's see. So we have that. This is clear. Oh, there's another question by Yuzaimi. Solution by Yuzaimi. Yuzaimi, are you there?
Ada.
Ada Jadi so I'll pass the screen to you please.
Nampak?
Nampak Yuzaimi?
Okey.
Alright.
Okey. Untuk aktiviti 2.21. Okey, soalan dia a very wide river juga. So rate dia bagi 6.5 meter cube per second per meter. Width dia 100 meter. Untuk bed slope dia, S0 dia 0.005 dan meaning dia N equal to 0.018. So untuk very wide ni R mendekati Y0. So R sama dengan Y0. So untuk formula dia Q equals to YV dan pecahkan untuk meaning formula untuk V 1/N, R kuasa 2/3, S0 kuasa 1/2. So untuk R ni tukar kepada Y0 sebab very wide. Okay, masukkan formula. Okay, pindah formula dia. Untuk Y ni pindah ke sini sebab kita nak cari Y0. And then masukkan formula dia 6.5 Q darab dengan N 0.018 bahagi dengan S0 1/2. Lepas tu dapat jawapan 1.655. So nak cari Y0 pindahkan pindah punca kuasa dapat 1.353 meter.
Okay, very good. Yuzaimi, thank you. Very clear. Thanks a lot. I'm very proud of you guys. You can present well. Thank you. Now, when you guys are presenting this, right, it just came through my mind about your test 1. Sometimes, all right, for test 1, sometimes I'll just give you coordinates, or for example, give you a cross section from side measurement. What you have to do is you have to find your own, section depth. That means dimension of your channel. So take your time. All right, don't rush. Make sure you get the dimension correct, because if you didn't get the dimension correct, then the following calculation will be affected by your dimension as well. Clear? Maksud saya tadi ialah kadang-kadang mungkin saya akan bagi soalan daripada kerja-kerja ukur di tapak. Jadi saya mungkin just bagi drawing di mana you kena tentukanlah dimensi channel tersebut. Channel tu mungkin bukan channel yang cantik yang macam kita belajar dalam kelas. Dia mungkin channel contohnya channel semula jadi di sungai tu, kita tahulah keratan dia macam mana kan. Dia mungkin tak seragam. Jadi you perlu tentukanlah, ambil masa, pastikan dimensi yang kita dapatkan tu ialah dimensi yang betul. Kalau tidak, dia akan mempengaruhi lah kita punya jawapan A dan juga B lah. Itu. Now, we'll continue with our lecture then. Alright. So there you have it. Okay, now.
Oh,
Okay.
doctor,
Yes.
I have a question.
Ah.
If I use the uppercase of Q equal, lowercase of Q equal to uppercase of Q divided by B, and then I use the formula AR power of 2/3 equal to QN over S naught power of half.
You can do it. You will
Can
get almost the same answer. You'll get it. Yeah,
all right,
don't
thank you.
worry. However, sometimes, Jordan, right? Sometimes you probably cannot solve it if the width is not provided to you.
Also, if the width is not provided, so I need to use that formula lah.
Yes, correct.
All right.
Sometimes you probably cannot get the solution lah. All right, because you probably will need the width. All right.
Okay, thank you, doctor.
Okay, you're welcome. Okay, then. Now let's go to the final subtopic of our chapter 2. Most probably at the end of this week, all right, on Wednesday, I'm going to sum up chapter 2. Now later on, okay, if you have time, go through assignment 2. You can start working on your assignment 2 already, and the submission date would be 1 week after we finish chapter 2 lah. So you may start already, because I think most of the question you probably can answer already. Try to do it yourself. I know probably you have answers from your senior, but if you don't do it yourself, you can't some of the question you don't understand, and that will not help you in your test or final exam lah. I have another thing to inform you. Our final exam question and also test question is not very direct, because we have the concept of doing question as open-ended as it is. That means the question is not direct lah, but once you grasp the concept in the class, you should be able to answer it. We try to avoid you from copying, you get answers from any website and things like that lah. All right. Now let's look at this best hydraulic section. Another thing, actually, there are few cases of academic integrity. I believe you probably have heard of it. There are a couple of students who have been, they were trial for getting answers from especially internet sources lah, because apparently some of the lecturers found out. That means actually we can actually request from this so-called homework helper websites to actually give us the IP address of those who actually request answers for particular question lah. We can actually do that. All right. So you have to be careful. All right. Let's continue. A non-erodible channel should be designed for best hydraulic efficiency. That means this is, when I say non-erodible channel, mostly is man-made channel lah. All right, like concrete, okay, or materials, channel lining which is non-erodible. Now, what is best hydraulic section? Best hydraulic section gives you maximum conveyance. That means maximum Q, when I say maximum Q, if you look at this expression here, you will expect maximum R as well, because R is actually directly proportional with Q. I hope you still remember, the channel conveyance K is actually Q divided by S naught to the power of half. Since the definition is the carrying capacity over longitudinal slope, and or minimum P. Remember, your R is actually A over P. If you have small p, all right, this term is going to increase. That means it will increase, your Q will increase proportionally as well. So therefore, that's why we said what will give you best hydraulic section is when your Q is maximum. Well, definitely lah, since your R is maximum and P minimum actually will give you Q maximum. Now, why do we need P minimum? You know, when the channel lining is minimum, okay, while your Q is maximum, you actually reduce the construction cost, excavation cost, as well as the lining cost. That's why it's known as effective section. Okay, cost wisely is reduced, but you can still convey as the same discharge. Okay, furthermore, you know, since your wetted perimeter or your area of lining is small, it actually reduces the friction force. So therefore, your Q is large lah, basically. Your velocity increases. Now, how are we going to get this? How are we going to get best hydraulic section? Here again, best hydraulic section is given when your wetted parameter is minimum. We can actually find when the wetted parameter is minimum. Look at here. This is an example of rectangular section. If you look at here, I have 3 columns here with different channels width. I increase it at interval of 0.5 meter. This is in terms of meter lah. Okay. Now, my y, okay, is A over B. All right. So here what I did is I plot y against wetted parameter. So therefore, my P is 18.5. Now, there's a purpose. You know, my first column is B first. I'll let you know later the formula that we are going to use. It's actually the same formula, which is the A and P. Let's look at this. So I substitute, you know, when B is 0.5, right? Okay, let A constant. Okay, my A is constant, which is 4.5. So what is happening now is my Y changes as well as my wetted perimeter. So for now on, the best section is when we keep the flow area constant. Okay, that is one of our assumption that we use lah. The flow area is constant. Now, when I plot, you know, when I have different B, and also that will make, you know, that will change my Y, that will affect my Y as well. So when I plot it, I'll get this kind of curve. Now, this curve here, okay, it will actually end up, you know, and giving me an inflection point. Inflection means, you know, the change of slope. All right, from negative to positive slope. This point here is the inflection point. All right, this is the inflection point here when there's a change where dp dy equals to 0. Okay, dp dy, sorry, dp dy is equal to 0. This one is P, okay. So this is my inflection point here. Now, this is where, you know, dp, when I set dp dy equals to 0, it will actually give me P minimum as well. So that is how the concept where we are going to find best hydraulic section is when we set dp over dy equals to 0, it will give us P minimum because this is a upward concave, upward concave. So you are going to get a P minimum value lah. All right. So let's look at this. Now, this table summarizes the formula for best hydraulic section. Where are we going to get, how are we going to get this formula? Is from this concept here where we set dP over dy equals to 0. It will give us the best hydraulic section. Now, remember in chapter 1, we learned about, this table here. This is the common, common formula to get flow area, top width, wetted perimeter, and so on for this section here. However, today, the formula that we learn is when we set dP dy equals to 0. That means the formula for best hydraulic section. So if we are using y here, all right, and I have introduced you y naught. Y naught is actually, this y naught is the depth for uniform flow. For this case, the effective section, we are using YE, all right? Okay, I hope you still get it. Okay, subscript E stands for effective. All right, so sometimes you'll see that I have, A subscript E, B subscript E. I'm using all those. It actually represents effective section. So let's in this subsequent slide, what I'm going to show you is how you are going to get to all this formula here. For example, the first shapes or section that I'm going to show you is this rectangular here. For best section of best rectangular section, I'm going to show that your B, just a second. Okay, your B, all right, if you look at here, rectangular, T is equal to B, right? Your B is equal to 2Y. And then your, of course, once your B equals to 2Y, your weather parameter will be B plus 2Y. That means 2Y plus 2Y for Y. And your flow area is B times Y. So 2Y plus times Y, you'll get 2Y squared. So all this is when, you set dP dy equals to 0. Okay, dP dy, I'm not going to go further. Okay, for trapezoid, you can actually set dP over dz equals to 0 as well. Okay, let's look at it. Let's look at the first section, which is the rectangular section. Okay, now I prefer to write this down. Okay, I'm going to show you. Step by step. Okay, now, okay, so what you have here is, all right, now our goal is to find the formula for best section of a rectangular channel. So what I have here is a rectangular channel. I'm going to find, of course, to find the dimension of the best section, we need the value of B as well as Y. What is Y? All right, so now the flow area is given as A equals to BY. Now, what we are going to assume is the flow area is to be assumed as constant. So I'm going to rewrite this as B equals to A divided by Y. Okay, it's the same formula. I'm just rearrange this. Then, This is the first formula. Then P, method parameter, is B plus 2y. Okay, so I'm going to substitute 1 into 2. Okay, I'm going to have P equals to A. I'm going to substitute B, Alright, A y plus 2y. So therefore, I can differentiate this differentiate P with respect of y. What I'll have here is negative A y squared, because this is actually A times y to the power of negative 1. So I have negative 1, this is negative 2, or divided by y squared, plus 2. So I differentiate P with respect of y, so I'll get this. Now, just now we said to get minimum P or best section, we'll set this equal to 0. So what we'll do is, I'm going to set this equal to 0 then. Okay. Okay. So A is, I'll do it one by one line. Okay, this will become 2. So A is 2y squared. Okay, so what we have here is, we also know that for, from here, okay, from here where A is equal to by, okay, we have 2y squared. So what is B then? B is 2y. We have shown that, A is equal to 2y squared, B is equal to 2y. Now, therefore, if B is equal to y for best section, best section, if B is equal to 2y, therefore P is B plus 2y. It will give us 4y. So what else? R, okay? If you look at here, which is A is 2y squared, I'm going to substitute here 2y squared, 4y. So this will give me y over 2. All right. So I have that. So I could, I could put here the subscript E, okay, because this is actually the most efficient section lah. All right. Okay. This. The others, no, I couldn't put like this. This is the normal formula, right? It doesn't has any. It's not the effective section yet. So if we go back to our formula, the table of the formula, right? You could actually, okay, if you look at here, the rectangular one, you'll see this is what we have found. Flow area 2y squared, weather parameter 4y, and then the hydraulic radius y over 2. I hope by now you know where this formula comes from. Okay, we just derived this, where we set dp over dy equals to 0. Now, the second section that I want to show you is the the trapezoidal section. Okay. Again, I'm going to show this. Did I close it already? Okay. Okay, so you are going to have the best section for trapezoidal. Okay, so all right then. Okay, so you probably wanted to know, okay, you know what is your width, bottom width, what is your side slope for best section. Now, initially, okay, we'll let A and Z to be constant because if we didn't set Z and A to be constant, then it's a bit difficult for our analysis. So what we'll do here is, okay, again, the same step. A is by plus zy squared. Okay, I'm going to rewrite this in terms of B. So I have A, okay, minus zy divided by y. Okay, you have that, Okay, so now P would be, okay, B plus 2y 1 plus z squared. I'm going to substitute, okay, 1 into 2, okay. So it will give me let A and Z to be constant. Okay, so Z is constant, A is constant. So I'm going to differentiate P with respect of Y. Then to find the best section, let dP over dy equals to 0. Now this is the formula of if since I said this is actually the most efficient area already. So A would be equals to y squared in bracket negative z plus 2 square root 1 plus z squared. This is a formula of A. All right. So the next one would be, okay, you wanted to find channel width, right? So what we have here is, so from here, from expression, let's say this is expression, sorry, I'm using this expression 3 here. Okay, from expression 3 here, I'm going to substitute my most efficient A into this expression here. Okay, look at this. This is y squared. Okay, so when I substitute my A, it'll become just y because I divided by another y already here. Okay, so then I multiply my y into, with minus z and with this expression. So I'm going to have this. So this is the expression of my wetted perimeter. Okay. In this case, A and Z are constant. Okay. I'm going to let you know what does it mean by A constant later. So let us proceed. R. Okay. Hydraulic radius R. Now, if you want to find width, right? All right, the bottom width, you will just substitute your best section, best or most efficient A here. All right, into this expression here, you'll get your bottom's width. So you have this A and P. I just do without the subscript E first. This is basically the same. It's just, I'm writing this first, but now I'm going to write this first. Okay, so that you'll see the similarity here. So what I did, because this is a multiplication, all right, expression. So what I can do is I can cancel it because it's a multiplication expression, right? Okay, so this will give me y over 2. All right, so there you have it, your best hydraulic radius for best trapezoidal section is when R is equal to y over 2. Okay, now this is the case. Remember that we say Z is constant. When I say Z constant means Z could be any value. Okay, sometimes the value, this could be any value that we give you in the question. It could be 2, it could be 1.5, we never know. But can we find the best Z value? What I mean is the Z for most efficient section? Yes. So what we are going to do is we are going to continue. Okay, our analysis just now. Okay, that means I could give you question where I give you Z value. Then what you are going to do is you are going to solve for B, Y, all right, using this, this expression here that we have already, obtained. But if I didn't give you this Z value, which is the side slope Z, you are and then I ask you to find most efficient, most effective channel section, trapezoidal section, then you are going to use the most efficient Z. All right, so there are two types of question in this case. So now how are we going to find most effective Z value? So let's say if Z is allowed to vary, that means the question probably doesn't give you any Z. That means you don't need to use a constant Z. That means we are going to find Z. All right. Okay. So you see, this expression here, I'm going to rewrite this A, the one that we have found earlier. So I'm going to rearrange this. I'm going to allow A to be constant as well. Sorry, this is negative, eh? Okay, so you have that, eh? Okay. So what I'm going to do is, okay, I'm going to substitute this. Let's put this as 4, equation 4. I'm going to substitute this into P. Where is my P? Okay. Into my P, into here, this formula here. Again, I'm going to put this as 4, this is 5, okay? So, substitute 5 into 4. Okay, so I'm going to have okay. Look at this. This has the same term, right? Okay. Now, I can combine this, all right, to become okay. Now, how do I do that? Remember, this is okay. I'll just write down in a simple expression. It's something like I have 1 over. Let's use x. X. Okay. Square root of x. Okay. Times x. So what I did here is I know that this would be 1 over x to the power of half times x 2 over 2. So when I combine this, I'll get x to the power of half. Okay, I hope you are clear. When I combine this, it'll give me x to the power of half because 2 over 2 minus 1 over 2, I'll get 1 over 2. So this is what happened in this case. Okay, so this, I assume this as x, my x lah. All right, it's the same thing, eh? So of course, square root a still remain there. So I have that ready. Now, what I'm going to do now, look at this. This expression contain only p and z. Of course, a is constant. So I'm going to differentiate dp over dz. So, of course, what I'll have here is this would be, I'm going to differentiate this. Again, I'm going to differentiate the internal part. This is the power, half of it. So this become 1 over square root. Times, I'm going to differentiate once again, this one. Okay, so you have that. So what you are going to get here is, okay, dp over dz. This can be further simplified, okay? So you are going to have, all right, this one, this guy here, all right? So this one times, right, 2z times a, so you are going to have okay, so you have that. So When you combine it, you'll have this divided by this. Then set dp over dz equals to 0. Okay. So again, you are trying to find p minimum. So when I set this equal to 0, I'm going to have, this is the numerator, this is the denominator. Okay, you have that. Okay, now I'm going to bring, if I bring this over here, I'm going to have only this one left. Okay, so I'm going to have, okay, so therefore, this one I bring it to the other side. I have basically it's 2az equals to a times this, but I cancel both a already, so this will become, okay, so I'm going to square both sides. I'm going to have, so I have, okay, because square root, right, both sides. So I'm going to, what I have here is the most of the side slope. All right, if it's allowed to vary, I'm going to, use the side slope of 1 over square root 3, which will give me the most efficient trapezoidal section. So this is how I found, I actually got my Z lah. Now, when you have Z already, what you can do is, okay, you are going to substitute to find your A. You are going to substitute to find your P as well. And of course, you can get your B lah when Z is equal to 1 over square root 3. Now, what you'll find here, you can try it, because I think I'm going to stop here. What I'll show you is, look at this. I wanted you to understand this table actually. Okay. You have this table that is provided. You have to know, you have to understand this formula here, okay, only applicable when you are using side slope Z equals to 1 over 3. When you substitute into the area P, it will actually give you this value, square root 3y squared, 2 over square root 3y. Now, in which case you can use this formula is when the question does not give you any side slope Z. That means you can choose your side slope. Of course, you are going to choose the most effective side slope, which is 1 over square root 3. However, if the question say or state a certain side slope, that means it's constant lah. All right, it doesn't matter 1 or 2 or 1 over square root 2, it doesn't matter. Then you cannot use this formula already. You need to use the formula, that has a equals to y squared minus z plus, square root 1 plus 1 plus z squared, that formula, okay? P as well. So be careful. However, we have shown that, even though the side slope is not 1 over square root 3, our hydraulic radius is still y over 2. Remember, we have showed that. So just be careful when you are using this table. This table or this formula here, all right, is when is applicable only when the side slope is 1/square root 3. If side slope other than 1/square root 3 is given, or you need to use other than this side slope, then you cannot use this formula already. So if you ask me whether you need to, you need to memorize this formula here, I would say either you memorize it or you go through the process, okay, of differentiating dp over dy. You set it equals to 0. It's not very difficult, if your your differentiation steps are correct, then you'll get this straight away. Okay, so I have shown you this. Okay, you can actually show, you can actually get this. You substitute z equals to 1/square root 3, you'll get this. Okay, okay, these are the one that in table lah. Okay, now look at this activity 2.24. You actually have two question here. One is when the side slope is constant. That means you have to use this z equals to 1.5. The other one is when the side slope is allowed to vary. That means, of course, you are going to use the most efficient side slope, which is 1/square root 3. So both are using this, are using different formula of A and P and also B. So you have to be careful. For activity 2.24, I'm going to go through with you on Wednesday. And then, okay, I have the solution here already. Okay, so I think I'm going to stop here. Okay, we are going to, oh, I forgot there's another subtopic here, channels of compound section. So we'll go through it on Wednesday then, all right? But I believe in your assignment, there is one question where you actually have to show, you have to prove for a triangular section. The best section for triangular channel would be when z equals to 1. You have to show that lah. Okay. So I'm going to end our class today right now. Do you have any question? Do you have any question for our class today?
No, Doctor.
No, okay. If you don't have any question, try out assignment 2. Probably on Wednesday. If you have question on your assignment 2, you can ask me on Wednesday as well. Okay, I'll see you guys.
Okay, Doctor.
All right, take care.
Thank you,
Okay,
Doctor.
Doctor. Thank you.
Thank you, Doctor.
Thank
Thank
Thank you.
you,
Bye,
Doctor.
Doctor.
Thank you, Doctor.
Thank you, Doctor.
Thank you,
Thank you,
Bye
Doctor.
bye.
Doctor,
Thank you,
attendance, Doctor.
Oh, okay. I actually
Link nak keluar.
saya bagi awal. Saya pun lupa nak share sekali lagi. Okay.
Oh,
Okay, dah.
oh, yang ni dah isi tadi, so tak payah isi lagi sekali kan,
Oh,
Doctor?
no, just one time.
Oh, okay, okay.
The
Okay, Doctor.
attendance one
Thank you.
time.
Bye.
Okay.
Thank you.
You're welcome.
Thank you, Doctor.
You're welcome.